Welcome to the class. Today we will start module 4, which covers convergence and divergence of infinite series and power series solutions of differential equations, under which we have three subtopics: Legendre's differential equation and its series solution leads to Legendre polynomial, Bessel's differential equation and its series solution leads to Bessel's function, and third one is convergence and divergence of infinite series. In the exam, your 7th and 8th questions are from module 4, under which 7th A and 8th A will be from Legendre's, 7th B and 8th B will be from Bessel's, 7th C and 8th C will be from infinite series. There may be change in some order. There may be change in the order in which the questions may appear in the exam. Let me come back to the syllabus part of it. Okay, in today's class, we will start Legendre's differential equation and its series solution. Let me look into the standard form of it. 1 minus x square d square y by dx square minus 2x dy by dx plus n into n plus 1 y equal to 0. Observe this equation carefully. We have not seen this kind of problems in our discussion. If you just remember from module 2, we have seen these three kinds of problems. This is differential equation with constant coefficients. This is Cauchy's differential equation. And this is Legendre's differential equation. I have just taken just the homogeneous part of it, as we are discussing homogeneous equation now. And here you can note that this equation is a differential equation with variable coefficients, but it is not going with any one of these two, which means I cannot make use of the methods which we learned for these three equations. So we need to think something different. But when we are thinking like this, so the idea comes from the Taylor series and Maclaurin series. Now, if you just remember what we got as the solution of these differential equations, you can note when you solve a differential equations, your solution will be the combination of trigonometric functions, exponential functions, logarithmic functions, or polynomials. You can note each of these functions can be expressed in infinite series form by using Maclaurin series expansion. If that is the case, okay, you are expressing the solutions of these equations in terms of trigonometric, exponential, logarithmic function, etc. And you can express each of these functions in infinite series form by using Maclaurin series. If that is the case, why don't we think of finding the solution of the differential equation itself in the form of an infinite series? So this idea is helped us in finding power series solution of the given differential equations. And this differential equation is in the form p naught of x d square y by dx square plus p1 of x dy by dx plus p2 of x y equal to 0. Now whenever you have an equation of this kind, so to employ power series method, we need to identify one condition, that is, we need to check whether p naught of 0 is not equal to 0 or not. If p naught of 0 is not equal to 0, then we claim x equal to 0 is an ordinary point, and we find the solution of such equations by using power series method. So now we will learn the power series method, which you can employ for any differential equation of this kind with the condition p naught of 0 is not equal to 0. But in this chapter, we are not interested in talking about any problems of this kind. We are interested in only one problem, that is Legendre's equation. Okay, let me check what we have for p naught of 0. In this case, p naught of x is given by what? 1 minus x square. Put x equal to 0 in it. That gives what? P naught of 0 is 1, which is not equal to 0. Which means x equal to 0 is an ordinary point, which means power series method is valid in this case. So, and this is how we assume the solution here. Y is equal to an infinite series a0 plus a1x plus a2x square plus a3x cube and so on. It's an infinite series where a0, a1, a2, a3 and so on. These are all the unknowns for us. So this infinite series can be put in summation form. That is summation r equal to 0 to infinity ar x power r. Okay, note if you put r equal to 0, you have your first term, r is equal to 1 gives this second term, r is equal to 2 gives this term and so on. Now I am assuming that our solution of this differential equation is this, which means this y should satisfy this given differential equation. If that is the case, I can find dy by dx, d square y by dx square. I will substitute them back in this and find these constants. Okay, this is what the method is. Okay, assume the solution of this equation in this form. Find dy by dx, d square y by dx square. Substitute everything in this. Equate the like powers of x. Okay, equate the like powers of x, and then by using those expressions, find these constants a0, a1, a2, a3 and all, and substitute back in this. This is what the method is. Now please keep this in mind. First let me try to understand how this problem works. You can just employ this method for any other problem, but from the syllabus you need not to think about any other problems here. Okay, this is our y. So now find dy by dx. Differentiation of a0 is 0. a1 is constant, differentiation of x is 1. Next, a2 is constant, differentiation of x square is 2x. a3 is constant, differentiation of x cube is 3x square and so on. Or if you differentiate this directly, this gives summation r x power r minus 1. That is, r is a constant, differentiation of x power r is r into x power r minus 1. But you can note the summation starts with 1 in this case, where here we had r is equal to 0. You people can note the reason. Here a0 was there. Here after the differentiation a0 is not present. So first term starts with a1. So which means I should write r is equal to 1 here. So that my first term is 1 a1 x power 1 minus 1. That is x power 0, which gives a1. Like that, if we just expand this summation, we get all these terms. Now find d square y by dx square. So differentiation of a1 becomes 0 now. Differentiation of x is 0. So we just get 2a2. And next 3a3 is constant. Differentiation of x square is 2x and so on. In infinite series form, this will be r into r minus 1 x power r minus 2. Okay, r into r minus 1 into x power r minus 2, and obviously summation starts from what? 2. Very good. So now let me substitute all these three expressions back in the given differential equation. So 1 minus x square into d square y by dx square. This is what I have written here. Minus 2x into substitute dy by dx, that is summation r equal to 1 to infinity r x power r minus 1, plus n into n plus 1, y is given by summation ar x power r equal to 0. Now let me try simplify this. Now 1 minus x square into this summation, which means 1 into summation, that is our first term, 1 into summation. Next one is minus x square into the summation. X square should be taken inside, that gives x power r minus 2 plus 2. So that gives summation r equal to 2 to infinity r into r minus 1 into er x power r minus 2 plus 2 just becomes x power r. Now take this x inside, that gives minus 2 summation r x power r minus 1 plus 1, that again becomes x power r. And there is no change in this expression, it is kept as it is. Now in the next step, now have a look at these expressions. If you want to take something common, You can note you have got x power r here, x power r, here x power r. Whereas in this expression I have got x power r minus 2. So I want to express every summation in terms of x power r only. Otherwise you can express everything in terms of x power r minus 2. It should be something, I just want to make it some common. For that, what can be done here? In this expression, in the place of r minus 2, I want r. So what I will do now, I am going for this operation of replacing r by r plus 2 only for this summation. For this entire summation, I am applying this. So if I apply this, what happens to this expression? Okay, let me just check that. I have just, instead of infinity, I have taken 5 here so that we can visualize the terms in the summation and we can understand it better. Now for r is equal to 2, it is 2 into 2 minus 1, a2, x power 2 minus 2. So this is my first term. Put r equal to 3, 3 into 3 minus 1, that is 2, a3, x power 3 minus 2, that is x. Put r is equal to 3, we get r equal to 4, we get this expression, and with the last term r, last value of r, we get 5 into 4 into a5 x power 3. Okay, if I just expand this summation, so this is what the terms are. Now I will do the operation which I was just suggesting you people. Replace r by r plus 2. So which means the summation becomes here r plus 2 equal to 2 to r plus 2 equal to 5. I should change here also. Wherever r is there in this expression, I should go for this operation. R equal to 2 to r is equal to 5 was there. I change this one. So here this becomes r plus 2 into this becomes r plus 1, and this is a r plus 2, and this is x power r plus 2 minus 2 becomes x power r. Okay, so now r plus 2 equal to 2 becomes what? Taking 2 to the right hand side, it becomes 0. Take this 2 to the right hand side, it becomes 3. So which means r is equal to 0, 1, 2, 3. These are the 4 terms this summation carries, this expression, and you just expand this and see whether this matches with this or not. Because I was telling you that this expression is not at all different from this expression. So let me just check out. If I put r equal to 0 in this, this becomes 2 into 1 into a2. This is what our first term. Put r is equal to 1, 2 plus 1 and 1 plus 1, that is 3 into 2 into a3 x power 1. You can note this term. We put r is equal to 2. So we can note 2 plus 2, 2 plus 1, a 2 plus 2 x power 2. And if you put r equal to 3, we have this expression. You can note that these two are exactly the same. So which means whenever you change the limits, whenever you change the value of r, it should not be in only one expression. It should be in the entire summation. If that is the case, it is not going to alter the values of the summation. It retains its value. So by employing this operation, then we will get summation r equal to 0 to infinity. This becomes r plus 2, r plus 1, ar plus 2, x power r. Here I have written infinity minus 2 as infinity again. Okay, so if you just come forward, to the next term, so these terms will remain as it is. There is no change in the values of these summations. Okay, done. Now in the next step, I will just erase this part. By keeping this expression, I will move forward. Okay, now I was talking about taking x power r common from all these summations, but I can't do that directly. What is the reason? The reason is here summation starts from 0, here the summation starts with 2, here summation starts with 1, and here with 0. So if all the summations begins with the same limit, I can take x power r common in that case. For that, what I will do now, I will just make the lower limit 2 in all the cases. For that, I will take first 2 terms out of it, first 1 term out of it, and here first 2 terms out of this. Now if I put r equal to 0, I will get 2 into 1 into a2 x power 0 is 1. That's our first term. Put r is equal to 1, write this term 3 into 2 into a3 x power 1. Now from 2 to infinity I will just keep the expression as it is. R equal to 2 to infinity, same expression. Now there is no change in this expression, write it. Here I don't want the first term r equal to 1, put r equal to 1 and take it out. That gives minus 2, 1 into a1 x power 1, and from 2 onwards it is kept as it is, minus 2 summation r equal to 2 to infinity r x power r. And if I come to this one, put r equal to 0, that gives n into n plus 1 a0 x power 0. R is equal to 1, that gives n into n plus 1 into a1 x. From 2 onwards it is kept as it is, 2 to infinity r x power r equated to 0. Now in the next step, this is what we are doing. I will just group the constant terms, coefficients of x and coefficients of x power r. So constant terms are, this is constant term, this is one more constant term, these two are grouped. Coefficient of x, one coefficient of x here and one more term here. I'm just grouping these three expressions together and I'm just taking x power r common from these summations. So that gives r plus 2 into r plus 1 ar plus 2, and here minus r into r minus 1 ar, and in this case minus 2 r ar, and here plus n into n plus 1 ar, x power r is equal to 0. Now I will equate this constant to 0. That is, after writing in this form, equate each expression in the left hand side. That is, equate coefficient of x power 0, x power 1, x power 2, x power 3, all these expressions to 0, because 0 can be written as 0 plus 0 into x plus 0 into x square plus 0 into x cube and so on. So that is why I am supposed to equate the coefficient of x power r to 0. So by equating coefficient of x power 0 to 0 in this case, we get 2a2 plus n into n plus 1 a0 equal to 0. That gives a2 equal to minus n into n plus 1 a0 divided by 2. Now by equating coefficient of x to 0, we get 6a3 minus 2a1 plus n into n plus 1 a1 equated to 0. Take this expression to the right hand side. Take this a1 common and simplify this expression to have this a3 is equal to minus 1 by 6 n minus 1 into n plus 2 a1. This can be shown. What you have done supposed to do, take a1 common and just simplify that expression. Just factorize the expression. That will give n minus 1 into n plus 2 a1. Next, equate the coefficient of x power r to 0, which means this entire expression is equated to 0. Okay, from these three terms I have taken er common. So that is what happens with this. Here er plus 2 is kept in the left hand side now. So that is equal to this entire expression divided by r plus 2 into r plus 1. Here I have just multiplied this r square minus r plus 2r. Okay, minus n into n plus 1 is written. So now you can simplify this. I will just take minus sign common from this and I will just make n square plus n. Here minus r square, and this is minus r plus 2r becomes what? Minus r. So now it will be just minus is taken common to have it as just r square plus r. Now you have got n square minus r square. What does it gives? N plus r into n minus r, that is a square minus b square, that becomes a plus b into a minus b. And what is remaining now? Plus n minus r, that is written as it is. From these two, n minus r is taken common, that gives n plus r plus 1. So this is what the expression, and you can note that this is the expression for ar plus 2, that is found in terms of ar, and it is valid for all the values of r greater than or equal to 2. So I know the value of a2, a3 and ar plus 2, and we can find ar plus 2 in terms of ar, and they are saying that it is, and we are saying it is valid from r greater than or equal to 2. Why we are mentioning this r greater than or equal to 2? because when you take r is equal to 2, this gives 2 plus 2, that is a4. Till a3 we have already found the values of the constants. From a4 onwards we are supposed to find it. Let me find them. If I put r is equal to 2 in this, that gives a4 equal to n minus 2, n plus 2 plus 1, 2 plus 2, 2 plus 1, a2. Okay, and do we know the value of a2? Yes, that is minus 1 by 2 times n into n plus 1 a0. Substitute in this. That gives n minus 2, n into n plus 1 into n plus 3 divided by 4 into 3 into 2. That becomes 4 factorial a0. I am just intentionally writing in this fashion. That is, I am writing from least number to highest number, n minus 2, n into n plus 1 into n plus 3. Now I will take r is equal to 3 in this. So that gives a5 value, that is equal to n minus 3 into n plus 4 divided by 5 into 4 a3. I know the value of a3, substitute that here. So I will write in the same fashion again. N minus 3 is the least number, next n minus 1, n plus 2 into n plus 4 divided by 5 into 4 into 6 is what? 3 factorial, which means denominator is 5 factorial. 5 into 4 into 3 factorial, that is 5 factorial. So this expression into a1. You can note that a2, a4 both are found in terms of a0. a3 and a5 are found in terms of a1. Let me find one more value. If I put r is equal to 4, I can find the value of a6, and in which we can note it is minus n minus 4 n plus 5 by 6 into 5 into a4. And I will just substitute the value of a4 and I will maintain the order. N minus 4, n minus 2, n into n plus 1 into n plus 3 into n plus 5 divided by 6 into 5 into 4 factorial becomes what? 6 factorial a0. Now like this you can find your a7, a8, a9, a10 and all. But I need not to make use of this formula anymore. Without using this formula also you can write these values. Just observe a2, a4 and a6. In a2 what happened? N into n plus 1 was there by 2 factorial. Now in this case note this one, n into n plus 1 is there, and towards the left of n we have got one expression, towards the right of n plus 1 we have got one expression. And how we got them? Subtract 2 from this, we get this, add 2 to this, we get this. And you do the same thing for this. You can note that subtract 2 from this, that gives n minus 4, add 2 to this, that gives n plus 5. Now if I want a8, can you guess what should be done? Subtract 2 from this, that gives n minus 6 into n minus 4. Everything will be there. After n plus 5 I should write plus 2 to this n plus 5, that is n plus 7 divide by, for 6 it is 6 factorial, for a8 it should be 8 factorial a0. Like this you can write for a10, a12, a14 and all. If I come to odd expressions, you can note it is, so this number was the number which is immediate left to n, that is n minus 1, and this number is immediate right to this n plus 1. So keep this in mind. If you just remember this one expression, you can just take off, you can just generate remaining all expressions. Okay, so here we had n minus 1 into n plus 2, and 6 is nothing but 3 factorial, we know that. And if you come to a5, I just explained you people, subtract 2 from this, that gives n minus 3. You place it here, n minus 1, n plus 2, add 2 to this, that gives n plus 4. Now can you guess a7? Yes, subtract 2 from this, that gives n minus 5, n minus 3, n minus 1, n plus 2, n plus 4 and plus 2 to this, that is n plus 6 should be written, divided by 7 factorial a1. Like this you can find a9, a11, a13 and all. Okay, that's fine. So like this, if you can find all these terms, what is the next step? So once if I can find few terms and if I just get an idea in which way it is going, you can just substitute these things back in the infinite series That is, this was our assumption. We assume thus this is the given solution of the given differential equation. In this assumption, substitute your expressions. I don't know what is A0 and A1, but I know A2, A3, A4, A5, A6 and all. I will substitute them. And after substitution, I will just group the terms containing A0 and terms containing A1 separately. So with that, this is what your solution is. Okay. The first term A0, this is what 1 into A0. A2 x square. I have written A2 x square. Here A0 is taken out. And A4, that is what I have written here, the positive sign, but A0 is kept outside. And it goes like this. I can write A6, A8 and all. And if I just take A1 out from the remaining terms, so here x will remain. From here A3, this is what A3. So 3 factorial, n minus 1, n plus 2, x cube. And similarly it is A5 x power 5, and these the expressions are written here. So this is the general solution of this differential equation. Okay, I hope you people are comfortable with this. So let me just recall what and all we did. Here we identified that in this equation, this is our P0 of x, which is not becoming 0 at x equal to 0. So we said that we are going to assume our solution in this form. And afterwards we found dy by dx, d square by dx square, substituted everything back in this equation. And afterwards, on simplification, we equated constant to 0, coefficient of x to 0, coefficient of x power r to 0. And we found the value of a2, a3 and ar plus 2. From ar plus 2 we found a4, a5, a6, all this. And then afterwards we substituted all these expressions back in our assumption to write general solution of the given Legendre's equation. Okay, this is what the method we have to solve the solution by using power series method. Now let me come back to this problem now. Okay, for this equation, I told you people that this is our general solution. But you can note A0 and A1 are arbitrary constants. Okay, if A0 and A1 are arbitrary constants, what is the order of this differential equation? 2. What I told you people, when you are solving the second order differential equation, we are expecting 2 arbitrary constants present in our general solution. These are those arbitrary constants C1 and C2 for us. So which means my general solution is in the form of y is equal to y1 plus y2. And where y1 is given by this expression and y2 is given by this expression. But keep this in mind, when we say c1 function of x plus c2 function of x is general solution of the given differential equation, you can note that each of these functions satisfies the equation individually. Okay, so this gives the complete solution of the differential equation, but each of this function, that is this y1 and y2, satisfies this equation individually. Please keep this in mind. Okay, that's good. Now these two are the two independent solutions of our differential equation. Further, now if I take this n is a real constant, that's fine. Now if I make this n a positive integer, let me see what happens. If n is a positive integer, okay, so let me take n is equal to 0. If n is equal to 0, you can note that here n is present, here also n is present, and we know that in every term from here onwards carries n. In every term from here onwards has n, which means that since n is 0, all these terms become 0, which means what is the degree of this polynomial y1 then? The degree of this polynomial is just what? 0. Now instead of that, if I put n is equal to 2, okay, if I take n is equal to 2 in this case, you can note that n minus 2 is present here. Once an expression comes into the picture means every term from that term onwards carries that expression n minus 2, which means that from next term onwards all the terms are zeros, which means that what is the degree of this polynomial? It is 2. When I took n is equal to 0, we got y1 is a polynomial of degree 1, whereas when I took n is equal to 2, y1 becomes a polynomial of degree 2. If I take n is equal to 4, in the next term what do we have? N minus 4 should be there in the next term. So from next term onwards every term becomes 0 when you take n is equal to 4, which means it becomes a polynomial of degree 4. Okay, in general what can be noted here? If n is a positive integer, in that case y1 becomes a polynomial of degree n. And if I come to y2, if I take n is equal to 1, you can note that n minus 1 is present here, and from here onwards every term carries n minus 1, so all these terms become 0. So y2 becomes what? A polynomial. It is a polynomial of degree what? 1. If I take n is equal to 3, from here onwards all the terms are 0, so it becomes a polynomial of degree 3. That's good. So which means that even in this case you can note that if n is a positive integer, y1 and y2 both represents polynomial of degree n. So depending on whether it is even integer or odd integer, if n is even integer, y1 becomes a polynomial of degree n, and if n is odd integer, y2 becomes a polynomial of degree n. Okay, so but keep this in mind. In this solution, if you take n is positive even integer, this becomes a polynomial. What about this? Is this a polynomial? No. This one is an infinite series. So which means when n is positive integer, it is made up of positive even integer. It is made up of two solutions. So one is a polynomial of degree n and the other one is infinite series solution. It is a sum of these two. Okay, when n is odd integer, this becomes an infinite series and this becomes a polynomial of degree n. You can note that even in this case, even when the n is an odd integer or even integer, you can note that our general solution of the complete solution is combination of a polynomial of degree n plus an infinite series or infinite series plus polynomial of degree n. Okay, that polynomial of degree n which satisfies the condition Pn of 1 is equal to 1 is called Legendre polynomial of order n. We are interested in talking about this Legendre polynomial. Is this fine? Please keep this in mind. It may be y1 or y2, any one of these two expressions. The expression which gives the this polynomials. When n is an even number, this y1 becomes Pn of x. When n is an odd number, y2 becomes Pn of x, provided this condition Pn of 1 is equal to 1 is satisfied. Okay, such functions are called Legendre polynomials of order n. And if that is the case, so you will be having one more function, right? Just now I explained you people. So this becomes what? This is if n is an even number, this is a polynomial of degree n. But what about this? This is an infinite series. That infinite series is called Legendre function of second kind and it is denoted by Qn of x. So if n is even integer, my solution y is written as this is Pn of x plus this is Qn of x. When n is odd integer, this becomes Qn of x and this becomes Pn of x for us, because this becomes a polynomial and this is an infinite series in that case. Okay, right now we are not interested in talking about Legendre function of second kind. We are just concentrating on Legendre polynomial of order n. Okay, so let me just go further for the discussion. Let me discuss the Legendre polynomials now. Okay, I told you people that y1, y2 both satisfies this differential equation, and these two depending on whether it's an even number or odd number. So these two are called Legendre polynomials under the condition Pn of 1 is equal to 1. So which means y1 and y2 satisfies this differential equations. Okay, now let me go further. If I put n equal to 0 in my y1, okay, see what happens this one. N equal to 0, it's an even number, I should consider this one. That gives all these terms are zeros, so which means p naught of x, y1 becomes p naught pn of x, because I told you that this is my Legendre polynomial now. Okay, Legendre polynomial when n is an even number. This is Legendre polynomial when n is odd number. Okay, now when n is equal to 0, I should consider this one. That gives just a naught with remaining terms are zeros. Okay, I need to find the value of a naught because this is an arbitrary condition. Make use of this condition. So p naught of 1 is equal to 1, which means put x is equal to 1 in it. That gives p naught of 1 is equal to 1, which is a naught. Which means what is the value of a naught? Which is 1. Substitute back in this. So my Legendre polynomial of order 0 is given by what? 1. P naught of x gives a Legendre polynomial of order 1. Sorry, order 0, and that is equal to 1. Now put n is equal to 1. So which means for n is equal to 1, which gives a Legendre polynomial. Yes, this expression gives Legendre polynomial. So it is p1 of x equal to a1x, because these terms are zeros. Use the same condition again. p1 of 1 is equal to 1. So put x equal to 1 in it. That gives a1. So which means a1 is again 1. Substitute a1 equal to 1 in it. So which means what is my p1 of x? Yes, it is just x. Further, if I take n is equal to 2, even number, I should make use of this. From here onwards, all the terms become 0. I will get first two terms. So that is y1, this becomes what? p2 of x. That is equal to a naught 1 minus, this is n is 2 now. It is 2 into 2 plus 1 divided by 2 factorial x square. But still the same condition holds good. p2 of 1 is equal to 1. If I put that, the left hand side becomes 1 equal to a naught 1 minus 3, x is 1. 1 minus 3 is minus 2. Take to the left hand side, a naught is equal to minus 1 by 2. So which means what is my answer is p2 of x is equal to minus 1 by 2, 1 minus 3x square. So minus is taken inside, so that becomes 1 by 2 times 3x square minus 1. Okay, further if I take n is equal to 3, in that case what happens? N equal to 3 odd number, I should consider this. From here onwards all the terms are 0, I will get only first two terms. a1 x minus of n minus 1, n is 3 now, 3 minus 1, 3 plus 2 by 3 factorial x cube. That gives x minus 2 into 5 divided by 3 into 2 x cube. This 2 cancels here, and the same condition holds good. p3 of 1 is equal to 1, which implies 1 equal to a1 x minus 5 by 3 x is 1. Take the LCM and simplify this. That is 3 is the LCM. 3 minus 5 divided by 3. That is minus 3 by 2. It is minus 2 by 3, and cross multiplication a1 becomes minus 3 by 2. Substitute this back in this expression. So it is minus 3 by 2 x minus 5 by 3 x cube. We just take this minus 3 inside. That becomes minus into minus plus. 3 cancels. We get 5x cube minus 3x divided by 2. Like this, you can find p4 of x, p5 of x, p6, p7 and on. But these functions, this pn of x, p2 of x, sorry, p1 of x, p0, p1, p2, p3, all these functions are what? Legendre polynomials, and we noted that these Legendre polynomials satisfies this differential equation, which means p0 of x satisfies this equation if I take n is equal to 0 in it. If I put n equal to 0, this is also a Legendre polynomial, sorry, Legendre differential equation, for which the solution is given by p0 of x, which is equal to 1. If I put n equal to 1 in it, this is also Legendre equation. For that one, the solution is given by p1 of x, that is x. If I put n equal to 2, p2 of x satisfies this equation. If I put n equal to 3, this p3 of x satisfies this equation. Okay, like this, in general, Pn of x satisfies this differential equation under the condition Pn of 1 is equal to 1. Okay, I hope you people are comfortable with this. So today, we discussed this Legendre's differential equation and its series solution, which led to the Legendre polynomials. In the exam, you need not to write up to here. If you just write up to this point, okay, whatever we discussed, after writing the general solution, okay, after writing the general solution, we wrote up to here. Okay, this much of this answer is enough from the point of your examination. If you write this one, it's good. This much is fine. Okay, so if the question is solve the Legendre's differential equation or find the series solution for the Legendre's differential equation which leads to Legendre polynomial, you're supposed to write up to here. And whatever we discussed after this, so that we discussed to give an idea what is a Legendre polynomial. So when does how this Pn of x satisfies the given differential equations. I hope you people are comfortable with this. Thank you all. In next lecture we will discuss problems on Legendre's differential equations or problems on Legendre polynomials. Thank you all.